Hello everyone. Now I'm familiar with this blackboard. I moved to our classroom to give my lecture today. I hope that you miss this place. I really gives me a great pleasure to be here again. Now today in this lecture, I'm going to talk about the second law analysis for thermodynamic cycles. So now please read the reading material in your book, chapter 6.3 through 6.5, and also 8.3. So today, I'm going to talk about, how to restate the second law of thermodynamics, right? By using the thermodynamic cycle point of view. And also, I'm going to talk about the quality of energy from the thermodynamic cycle point of view again. So at the end of this class, I really want you to be able to answer these two questions. So first question is, how can we restate the second law of thermodynamics using the thermodynamic cycles? So we are going to talk about two restatements. And the second question is about how can we define perpetual motion machines that I'm going to talk about for today. Then we are going to move on to the next question that I didn't write there. Then how can we understand the quality of energy? Now, I hope you remember this statement about the second law of thermodynamics. Okay, so way before when I first introduced the second law of thermodynamics using the entropy to you guys, I stated the second law of thermodynamics this way. So in an isolated system, entropy cannot be destroyed, but can be either be created in a reversible process or remain the same in a reversible process. So that is what we understand and how we memorized the second law of thermodynamics. But can you really restate that same second law of thermodynamics using the thermodynamic cycle? So in order to do so, I'm going to ask one question. Now, the first question is, can we make a heat engine with 100% thermal efficiency? Now, in order to answer this question, I draw on the blackboard these schematics. So now we have thermal reservoir and we have a heat engine. So cycle means heat engine. Now, we want to have 100% efficiency heat engine, meaning that we have heat input from high temperature heat source with QH. Then this heat engine gives us certain net work out. However, in order to maintain the 100% efficiency, all the amount of heat input should be directly converted to W net out, meaning that there should be no heat out to low heat sink. Okay, so based on the thermal efficiency definition, we have W net out divided by QH, that is 100%. Now, is it possible to make such a heat engine? So in order to answer this question, let me try to apply the second law of thermodynamics. When we consider your heat engine as your system, the second law of thermodynamics gives us change of delta S is equal to 0 because that's a cycle. That is because of QH divided by TH plus entropy generation. Now, from this second law of thermodynamics, now what we have is entropy generation should be equal to minus QH over TH. So what it means is that now QH should be positive and TH should be also positive. But because of this negative sign, your entropy generation should be negative if we can make a heat engine that has a thermal efficiency of 100%. So what can you tell about that? Is it really possible? Can you really make the entropy generation negative? The answer is no. So that is not possible. Okay? So what it means is that we can never ever make a heat engine that has thermal efficiency of 100%. We just try to prove that there's a no heat engine that has a thermal efficiency of 100%. Okay, by using the second law of thermodynamics. And Kelvin and Sir Kelvin and Planck also thought about that. So they restated the second law of thermodynamics such a way. So they said it is not possible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount work. Okay? So let's make it a little simpler statement. So now, as you see in this slide with red color, now the second law of thermodynamics states that no heat engine can have a thermal efficiency of 100%. So if someone else claims that they could make heat engine with 100% thermal efficiency, simply that is not correct. That is totally wrong because they violate the second law of thermodynamics. Now, let us move to the second question. Can we transfer heat from a low temperature reservoir to a high temperature reservoir? How can you answer this question of question 2? Is it really possible to transfer heat from low temperature reservoir to high temperature reservoir? In order to answer this question, I already drew 2 reservoirs. One is TH in terms of temperature. The other one maintains at temperature TL. Now let me assume that TH is higher than TL. So in order to prove, or in order to answer the question, let me assume that we have a cycle, a dummy cycle. Okay? Dummy cycle. Okay? But it doesn't have any heat input, doesn't have any heat output. Meaning that all heat that is transferred from the low temperature reservoir to the cycle in terms of a Q is directly moves to TH with the same amount of Q. And let me just try to think about what happens in terms of energy balance in the cycle and how can you write the second law of thermodynamics. In order to do that, let's assume that your cycle is your system. Then second law of thermodynamics can be written as that. Because we are talking about cycle, the entropy change of your cycle should be 0. That is because of Q over TL minus Q over TH. Okay, these are entropy transfer from the low reservoir to system, and now from system to high temperature reservoir. Then we should have entropy generation. So from this equation, entropy generation is equal to Q over TH minus Q over TL, which is same as Q times 1 over TH minus 1 over TL. So, what is the sign of this entropy generation? Because we already assumed that TH is greater than TL, if you look at this term, 1 over TH is smaller than 1 over TL. What it means is, from that equation, we conclude that entropy generation should be negative if it is possible to transfer heat from low temperature reservoir to high temperature reservoir. Now, that is not possible. So it is not possible to transfer heat from low temperature to high temperature. Clausius actually thought about this, in a very earlier time. And he stated the second law of thermodynamics by using this concept. So what he said is that, so he said that it is not possible to make a device that operates in a cycle and produces no effect other than the heat transfer of heat from a lower temperature body to a high temperature body. I know that statement sounds pretty, complicated, and it's pretty hard for you to understand it. So let me rephrase what he says to more simpler sentence. Now, can you look at the red color sentence? So Clausius' statement of the second law of thermodynamics is heat cannot be transferred from a low temperature to a high temperature. Okay. So now we have three statements of the second law of thermodynamics. So the first statement about the second law of thermodynamics is that about the entropy. So in an isolated system, entropy cannot be destroyed, but can be increased, can be generated, or maintained the same. Now, the same content, same physics of the second law of thermodynamics can be restated in terms of efficiency of the cycle. So the second law of thermodynamics states that it is not possible to make a heat engine that has 100% thermal efficiency. The last statement about the second law of thermodynamics is that heat cannot be transferred from a low temperature to a high temperature.